Hey, welcome back! This is the last video out of the 5-video series for Velocity Time Graph, and I kind of snuck in Acceleration Time Graph. Here in this video, in the last part, we will just talk about Acceleration Time Graph. We're going to tie all the pieces together, hopefully, and I will do a quick summary at the end of the 5 videos that you've just watched. So let's begin! Okay, so now we know, and I'm going to use this little diagram here again. We know that for a position time graph, if we grab the slope, we got velocity out of that, okay? On the velocity time graph, if we find a slope on a velocity time graph, we get the acceleration. In the last video, we found that if we find the area underneath a velocity time graph, we got the displacement again, and I could change that to a D if you prefer D over P. Now in this last video, we are going to talk about acceleration time graphs and how everything fits together. In fact, I want you to predict what would you get if you find the area underneath a velocity time graph. Okay, so let's get to that, okay? Now, in this video, I'm going to talk about how do we draw a acceleration time graph given a velocity time graph. You already know how to find the slope on a velocity time graph to give you the quantitative value for your acceleration. So in this first part here, I'm going to show you what how to find the acceleration, how to draw the acceleration time graph from your velocity time graph. The second part, I will go into what this area really means, what the area underneath a acceleration time graph means, okay? So let's get to it. Last video, we can do it. All right, similar to before, when you ever want to draw a graph or you're trying to break down a graph, good idea to split your graph into segments. And here we just have that. Here we have a straight line, then the line changes, meaning we have since the slope abruptly changes, we're going to break the graph down there at the 8-second mark. And I'm going to draw this on my acceleration time graph to remind me that's what I did. And for the first segment, let's start off with the first segment here. Notice it's just a straight line, meaning we have a slope of 0. And whenever we have a slope of 0, we know the acceleration is 0 as well. Now, when we draw that on our acceleration time graph, since the acceleration is constant, and again, as I told you before, I wouldn't be worried about dealing with a non-constant acceleration, so that the acceleration here is just a straight line across the 0 mark for a 0 acceleration. The second part, we have the graph tapering upwards here at an angle, so we need to find the slope of this line to grab our acceleration here, and we know that slope is rise over our run, and our rise is, the x-axis is going up by 1 every box, so I can just count the boxes, 1, 2, 3 for our rise. Positive 3 meters per second divided by our run, and same thing on the x-axis, every box is represented by 1 second based on our scale, so I just count by 1. 1, 2, 3, 4, 5, 6, 7, 8. 8 seconds, giving us 0.375 meters per second squared. Okay, so that's our acceleration for our second part. If we want to draw that on our acceleration time graph, it's going to be a tiny number, less than 1, and it's constant, meaning we'll have a straight line, and that's going to be somewhere around there, okay? Not going to be perfect. Kind of goes to about there for the graph above. And this is too small to even show dotted lines, so I'm just going to leave it as is, okay? So here's my acceleration time graph. It's not very exciting, is it, compared to a velocity or a position time graph? And that's just what it is, because oftentimes you might not even see acceleration. Now here is where I want to talk about the area underneath your acceleration time graph, and what does it actually give you? If you said here, or if you thought it gives us velocity, I'm going to tell you, we need to be more specific than just velocity, and this is why it is. Let's do a quick analysis here. So let's actually go and zoom in here where we have a area that we can work with. Probably this one, because that's going to give us a area of 0. So let's use this guy over here. So let's say I want to calculate the area underneath this graph. From 0 to, let's just say, what is this? 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 seconds. So this is exactly 8-second difference here between this 8 second and 16. And just to remind us, is 0.375 meters per second squared, okay? So if we want to find this area here, for a rectangle, this is our width times our length, and our width, let's say it's how high the rectangle is, meters per second squared, times the length, which is 8 seconds, and we get here, and fine, I'll use a calculator so we can see, 0.375 times 8, giving us 3, okay? That's 3. And what are the units? Well, let's do a quick check. We have meters per second squared times seconds, and if we did that, one of the seconds cancels out, leaving us with 3 meters per second. So, hey, look! It gives us the 3 meters that we found up here above when we talked about this height or the rise in our slope. But what does that actually mean? What does this rise mean for our slope on a velocity time graph? If you said change in velocity, you are correct. So if we take a look on this graph here, why is it change in velocity? Because this object went from 4 meters per second to a total of 7 meters per second. So here we have a change in velocity of 3 meters per second. So what this 3 meters per second really means is the change in velocity, not just velocity itself. And how does this mean? What does this mean in the context of everything? Recall that acceleration, the definition of acceleration, is change in velocity over the time. So let's try to rearrange this a bit. If we moved time to the top, we get acceleration times time is equal to change in velocity. This change in velocity is when we calculated the area, A times t, A for acceleration, t for time, giving us change in velocity. So from a dimensional analysis perspective on a graph, when we geometrically multiply the two sides of the rectangle, this is what we got in terms of the actual quantity for change in velocity. Isn't that cool how everything just makes sense? See, that's the amazing thing about physics, is that everything makes sense and it's all very logical, and it's everything's connected, and the concepts are very tied closely together. Okay, so that's the area underneath the graph of acceleration time graph. It gives you the change in velocity. So now I would like you to try this example below, and to use the velocity time graph to find the acceleration time graph. I think the time should be the right one. Okay, so give this a try. Okay, now it's time for me to go over the solutions on Quick Play. Notice the graph here is broken up at the 3-second mark, so I'm just going to find the slope of the first segment first, rise over run. We're descending by 10 meters per second over 3 seconds, giving us negative 3.3 meters per second rounded up to 2 sig figs. Second part, I picked that point in the origin for easy calculation's sake. Now we have a positive slope of 0.6 meters per second squared. Drawing this on the acceleration time graph, I'm breaking it down at the 3-second mark and drawing the negative 3.3 on my graph there, and the 0.6 meters per second all the way up to the 16-second mark there. Okay, so here we have this last example. Now notice these graphs were borrowed from a previous question that I did before, so I did go through and calculate everything just to do a quick reminder of how to find the slope on a velocity time graph. But if you just took the values that you found earlier in this particular lesson set, then good for you. Haha, sneaky you. You were able to skip a few steps and just directly graph the acceleration time graph. First, we have a constant acceleration of negative 3.3, rounded up to 2 sig figs roughly. And then we jump back up to a positive acceleration of 0.6, which I roughly drew there as a straight line. Now, this is the end of the whole series of lessons on velocity and acceleration time graph. So I know this was a lot of material. It's a lot to take in, and if I want to let's just go through every single part of this video, every part, just to summarize what we learned in every part and the key things. So in the first video, we talked about no acceleration for uniform motion. How do we go from a position time graph to a velocity time graph? The key thing was to break everything apart. So break the graph into chunks and use every part of the chunk to find that particular velocity to get your the slope to get your velocity time graph. Okay. Then we jumped into acceleration. So when we have a non-uniform motion, what do we expect on a velocity time graph? What we would see as a curve on a position time graph translates into a straight line on a velocity time graph. And this is where we learned about finding the slope on a velocity time graph gives us our acceleration value. So this is this was the second video. And because of that, we were able to know that as we find the slope of every corresponding graph, we kind of step up to the next level. Displacement on a slope on a displacement time graph gives us velocity. The slope on a velocity time graph gives us acceleration. Then we dealt with cases, we then went back to see what acceleration, how do we find the velocity time graph when there's acceleration on a position time graph. And because it is, because we're talking about curves and I don't expect you to quantify curves, we can draw all of this very roughly as in a sketch. So we don't need to be looking at the numbers here, but the relative values, we can still kind of estimate that. So this was the second part of the video. This was the third video looking at that. The fourth video was a bit more meatier because before we went forward, we went to the next level by looking at the slope. In the fourth video, we started looking back. So what happens if we want to find displacement from a velocity time graph? We needed to find the area, okay? And that you needed to look at the region that's between the graph line and the x-axis, being careful that when a graph goes below the x-axis, you need to find the area from the line all the way back to the x-axis. So it might be, it might seem a little counterintuitive to what you might think the shape looks like. Continuing on, in the last video, what we did is we looked at acceleration time graphs to make sense of everything. Yeah, the missing piece of the puzzle is that if we take the area underneath of acceleration time graph, we get the change in velocity, not the velocity itself. And that kind of summarizes everything that we looked at in this particular 5-video lesson. So if you want to take away anything from these 5 videos, you can take away this little diagram that we have here. If you step up to the next level, you grab the slope of each corresponding graph. If you want to step down or go back, kind of going back from acceleration velocity to displacement, you find the area, okay? So hopefully you learned something from these 5 videos. Please, if you feel free to rewatch any of them just to do a quick recap. And the only way to get better at this or to really grasp everything is really doing practice. A lot of practice. It's very tricky stuff, especially it's our first time looking at it, but please be patient with yourself, and it's going to be hard for everybody, but at the end of this video, at the end of this series, once you start to get better at it, you'll feel really good about yourself. And also, these graphs, the concept of these graphs, find the slope, etc., the idea of that will come back again later in the course, and also in later parts of future courses that you might take. So please take the time, all right? Well, thank you for bearing with me with this video, and you did a fantastic job getting through all 5 videos. And if you did all the practice and you took the patience for yourself, thumbs up to you, pat yourself on the back, do whatever, go for a coffee break, eat some cake, whatever that is. You deserve it, okay? I will see you back in class and do more practice. Again, thank you very much, and great job, everyone. Fat Mama Physics signing out.